This is part 2 of lesson 1 of unit 2, and we are writing equations of tangent lines. Remember that writing the equation of a line requires a point and a slope. It follows that we should be able to write an equation for a tangent line through a given point, since we can find the slope through our limit process, and we're given the point, or at least the x-coordinate. So the form that we want to use is point slope, and we usually solve it for y. So it looks a little different than the normal point slope formula. Usually it looks like this. Y minus y1 equals m times x minus x1. But in this case, that y1 gets moved over to the other side, so that we do have a typical equation with y equals. So we're asked to write an equation of the tangent line for y equals x squared at the point 3, 9. Well, the nice thing about this is we did this, found the slope for this equation in example 4, which was the end of the first video. So you can watch the first video if you don't know where we got this. But the slope is 6, is what we found in the last problem. We're told that x1 is 3 and y1 is 9. So we really just need to substitute for x1 and y1. So we get that y equals our 6 times x minus 3 plus 9. So that's the end of that example. Usually you don't do the slope in a separate problem. Usually you're given example 5 as a problem, and you have to find the slope first and then write the equation. Since the slope of a tangent line is a limit, this would be a good place to talk about what if the limit doesn't exist. Because the slope of the tangent line might not exist because there's an asymptote, or it might be oscillating, or there's a jump discontinuity, or you might have a tangent line that has a vertical slope. If the tangent line exists but it has an undefined slope, so that would be specifically for a vertical tangent line, we use the following definition. If f is continuous at a, so we have a continuous function, it just so happens that we have a vertical tangent line. The limit as h approaches 0 of f of a plus h minus f of a over h is positive or negative infinity. Then the line x equal a is a vertical tangent line to the graph. So an example of that, if you're just curious, would be if we had a absolute value graph. So here's our absolute value graph, and we look at the point x equals 0. That is, in fact, the y-axis. The y-axis is the vertical tangent line, x equals 0. So here we have a point, and at that point, the only place we can draw a tangent line is straight up and down, so we end up with an undefined vertical tangent, such as that. Okay, so another term that we're going to see a lot is a normal line. What it means to be normal, it means to be perpendicular to the tangent line. So to find the slope of the normal line, what we're first going to do is find the tangent line slope and then use the opposite reciprocal. Then we can write the equation of the tangent line. So for example, let f of x equal 1 over x plus 3. And we're going to use the definition of the limit definition to compute the slope. And then after that, you'll see in part B, we're going to find the slope, and then we're going to write the equation of tangent line, the equation of normal line, and then we're going to estimate a value. So this is a typical slope question. Okay, so we're going to use our limit definition. So we're going to take the limit as h approaches 0 of f of a plus h minus f of a all over h. So we don't know what a is yet, so we're going to keep a in the equation. So this is going to be the limit as h approaches 0 of 1 over a plus h plus 3 minus 1 over a plus 3. This is all divided by h. Okay, so to simplify this, what I'm going to do is make a common denominator in my top two fractions right here. And I'm going to combine those, and then I have simplified the entire fraction. So when I make a common denominator, I get a plus 3 minus a plus h plus 3, and that's over my common denominator, a plus h plus 3 times a plus 3. And of course, the whole thing is still over h. So combining like terms, simplifying a little more, we're going to have the limit as h approaches 0. So I'm going to change the signs of everything inside here. So the a's will cancel because I'll have a positive a and a negative a. The 3's will cancel. So the only thing I have left in the numerator then is negative h. Negative h over my common denominator, a plus h plus 3 times a plus 3. And this whole thing is over h. So the h's will cancel. So I'm left with the limit as h approaches 0 of negative 1 over a plus h plus 3 times a plus 3. So now I can do a direct substitution because I won't have an undefined form. So the slope of my tangent line will equal negative 1 over a plus 3 times a plus 3, which is negative 1 over a plus 3 squared. So that's our final answer for our m right there. Okay, so now we found we use limit definition to find the slope of the tangent line. Now we want to find the slope of the curve at x equals 1. So what that is telling us is that a equals negative 1. So we're going to substitute negative 1 in for a. So we have m equals negative 1 over a plus 3 squared. So this is going to become m equals negative 1 over negative 1 plus 3 squared. And when we simplify this, we get negative 1 over 2 squared. So we get negative 1/4. Next, we're supposed to write the equation of the tangent line there. So I need to know what f of 1 is, f of negative 1, which is going to be 1 over negative 1 plus 3. So that's going to be 1/2. So I need that. That's my y1. Okay, so we have y equals m times x minus x1 plus y1. Oops, yep. So that becomes y equals negative 1/4, our slope, times x minus a negative 1, so x plus 1, and then plus 1/2. Next, the normal line. So the slope of the normal line is going to be the negative reciprocal of our slope, so that's going to be positive 4, because our slope of our tangent line is negative 1/4. So we're going to flip it and change the sign. So we're going to do the same thing. The point hasn't changed. We are still at negative 1/1/2 because we're at the same x value. So our equation just changes by the slope. It's now 4 times x plus 1 plus 1/2. And then finally, we're supposed to use the equation in part C to estimate the value of x equals negative 1.1. So that's just a simple substitution. So we're going to do y equals negative 1/4 times negative 1.1. Whoops, didn't want to do that. Negative 1.1 plus 1 plus 1/2. And when you figure that out, you get 0.525. Okay, so that's a typical example. All right, now if you notice, look, you're going to get to use your calculator here. Okay, so let's do a summary here. So we are summarizing For given this parabola, which has the function f of x equals 4x minus x squared, we want to know how fast is the graph of f of x changing at x equals 1. So that is, if you're asked a question like that, you're being asked, what is the slope of the tangent line at x equals 1? We want the rate of change, so we need a slope. So we're going to use our calculator to evaluate the average rate of change between f of 1 and f of 1.001, and to be sure to show the difference equation. So what we're doing here is we're going to do f of 1.001 minus f of 1 over 1.001 minus 1. Now those values you can just substitute right in for x here, and that's why you might want your calculator to square those and put them together. So I'm not going to show that. I did it already, so I'm just going to write the values here, and I'm going to write out a lot of decimal places here. So f of 1.001 is 3.00199 minus f of 1, which is 3, and the difference between 1.001 and 1 is 0.001. So we get a slope of 1.999. So our average rate of change is going to be approximately, because I did round it, 1.999. Okay, so now we want to find the average rate of change between our original point at 1, f of 1, and what if we move over just a tad, h away? So we're going to use our difference quotient for that. So we're going to do f of 1 plus h minus f of 1 all over 1 plus h minus 1. So we get, when we put 1 in, we're going to do 4 times 1 plus h, and then we have minus 1 plus h squared. That's the first part of this difference quotient. And then minus, we already figured out f of 1 to be 3, over, and the 1's will cancel here, we'll just be left with our h. So this simplifies when I multiply everything out. We have 4 plus 4h minus, and then when we square that, we get 1 plus 2h plus h squared minus 3. And this whole thing's over h. So that gives us 4 plus 4h minus 1 minus 2h minus h squared minus 3. Now here's the moment of truth. Does everything that doesn't have an h cancel out? So I have a 4 minus 1, that's 3, minus 3, and that is 0. So yes. I also have like terms here. I can put those together. So my difference quotient simplifies to 2h minus h squared over h. And simplifying that, I get 2 minus h. Now, a couple things here we have to make sure we say. So our average rate of change at just a teeny bit away from 1 is 2 minus h. But remember, h cannot equal 0, because then if it did, going back, we'd have an indeterminate form here, and we would never get to this point. So we have to make that stipulation. Okay, so next part says, what happens to the secant lines between the points as h goes to 0? So in other words, we want to take the limit. So now we're not going to actually let h get 0, but go to 0, but it goes to 0. So that's the key there. It's going to 0. So we're getting arbitrarily close to 0. So our slope then is going to be the limit as h approaches 0, and we could use our simplified form, 2 minus h, because we already did all the hard work. And when we do that, we can substitute, and we get 2. And I know that seems kind of weird, because I said earlier that h couldn't be 0. But I mean, if h were like 0.00000001, it would still be so close to 2, because remember, we're approaching 0. So what number is our slope approaching? It's approaching 2. So that's why we can do the substitution there. And then finally, we're supposed to find a general formula for finding slope at any point. So this is the key. You should be able to do this for any function, because if you notice, we don't have any a's in here. We don't have a specific point. We're using x. So we should be able to come up with a formula with no a's in it all, no values. Okay, so we're going to go back to the beginning and start with our limit of our difference quotient. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x. So substituting, we're going to do 4 times x plus h minus x plus h squared minus our f of x, which is 4x minus x squared. And that whole thing, the bottom simplifies to h. Okay, so we get the limit as h approaches 0. Expanding everything, we get 4x plus 4h. And I'm just going to keep this step because you want to make sure you don't lose those minus signs. They could be troublesome to find later if you drop your parentheses too soon and forget to change one sign of something you squared or cubed or something like that. Because if things don't cancel out, that becomes very frustrating. Okay, so I'm not going to show the part where I distribute that because of space, but technically what we do here, that's going to be a minus, that's going to be a minus, that's going to be a minus. And then we can see that our x squareds will cancel. We have a 4x here and a minus 4x, and everything else has h's. We just want to make sure we have the right signs. So we have the limit as h approaches 0 of 4h minus 2xh minus h squared, and this is over h. Factoring out an h, we get the limit as h approaches 0 of 4 minus 2x minus h. Now I can do the substitution. So I get 4 minus 2x. So this is where we're going to use our derivative notation. The slope of our tangent line, we usually use m if we're talking about a specific point. But in general, for our function, f prime of x is going to be 4 minus 2x. And this should work for any x that's available. And so there we go. That's our first real derivative. I hope it feels good. All right, so that's the end of the notes for section 1, and we'll be doing more with derivatives as we go through Unit 2.